is all about aqueous solutions. Let's do the fundamental definitions first. A solution is a special kind of homogeneous mixture. Now, we already covered mixtures earlier in the text. Mixtures are two or more components occupying the same space. And the deal with mixtures is that they're not interacting chemically. So those components inside the mixture can be separated. A solution is a special kind of homogeneous mixture in which you cannot visually see where the components are, that the components are so finely dispersed that they are not visible to the naked eye. So a solution is a homogeneous mixture, mostly going to be in liquids. There are exceptions. You can do solid solutions, you can do gas solutions, although truly gases behave as mixtures, not as solutions, where the components are not discernible. And we can't separate a solution by filtration because the particle size is so small that they pass through the filter. In terms of definitions of what's going on, we have a solvent. The solvent is the major component. And for us, in this chapter, the majority of the time, that's going to be water. And then a solute. And the solute is the minor component. And the solute dissolves in the solvent in a process called solvation. Solvation is the actual process of dissolving. So here are a couple of examples of solutions. Salt dissolves in water. And visually, if we had two beakers, and one was pure water and one was salt water, visually, we could not tell the difference. Oxygen dissolves in water. Fish are able to breathe underwater through their gills because of the dissolved oxygen that's in the water. And alcohol, also a colorless liquid, dissolves in water, a colorless liquid. And you cannot discern which of these is present. Okay. Now, we're probably aware that if I want to add more salt into aqueous solution, temperature has an effect there. That if I increase the temperature, increasing the temperature allows solids more solubility in liquids. However, the exact opposite is true for gases. Gases are more soluble in liquids when they're cold. Many ionic compounds dissolve in water, and when they do, they dissociate into their individual ions. So sodium chloride, salt, when it dissolves in water, splits into sodium cations and chloride anions, and it does that 100%. That makes this a strong electrolyte. An electrolyte is something in solution that carries a charge, carries a current, and you might be aware that pure water does not conduct electricity, but salt water does conduct electricity. It's the ability of this separation of charge here between the plus and the minus that allows electrical current to flow through. Now, not all ionic compounds are equal. Some materials, like hydrofluoric acid, when they dissolve, only put a little bit of ions into solution. And in those cases, we call these weak electrolytes. And there are a handful of rules for how to identify strong electrolytes, and that's next. These are the solubility rules for ionic compounds. All sodium salts are soluble in water. In fact, everything in group 1, all the metals in group 1, sodium, lithium, potassium, also rubidium and cesium, although then you're not likely to find those in nature, soluble in water. Also completely soluble in water, all ammonium salts. All nitrate salts are soluble in water. All acetates are soluble in water. Most chlorides, but not all chlorides, the chlorides of heavy metals like silver, cadmium, mercury, they are not soluble in water. Most sulfates are soluble in water, again with the exception of the heavy metals, the lead, the mercury. Those sulfates are not soluble in water. Also, barium, which is in group 2, makes a very insoluble salt. Hydroxides. Most hydroxides are not soluble in water. But of course, if you are the hydroxide of a group 1 metal, then you get to be soluble in water. So if there are two things on the list of rules and they conflict, the one that says you are soluble, that one wins. So at some point we're going to want to measure how much material I have dissolved in solution. We have a couple of different ways of describing that. The simplest is called solubility, and that is just mass per volume. And those terms are not strictly defined, but it typically means grams per milliliter or grams per liter. Concentration. And concentration takes the concept a little bit further, making it more useful by turning my mass of solute into moles. And so concentration is moles per volume. And in terms of concentration, there are two important distinctions. Your concentration can be defined in terms of molarity, and molarity is moles of solute dissolved per liter of solution. Notice here it doesn't say solvent, it says solution. What this takes into account is that if I had a container that held exactly 1 liter and I filled it completely with the solvent, when I added my solute to dissolve, it would, because the solute has its own volume, it would displace some of the liquid. So this liter of solution contains the volume of the original solute inside. So when we make solutions in terms of molarity, we start with an empty vessel. We put the solute into the vessel first, and then we make up the solution up to 1 liter. Okay. A slight twist on that is called molality, and molality is different than molarity in that this is moles of solute per kilogram of solvent. Now, because we're dealing with water, 1 kilogram of water, because it has a density of 1 kilogram of water is equal to 1 liter. So you might think that these two are the same, but this one says solvent and that one says solution. So this is, you take a mole of your solute and you add it to an existing kilogram or liter of the solvent. So this solution actually occupies more volume than that one does. And the distinction why we need both is that if you were to perform an experiment that you wanted to track at 2 different temperatures, this one is not susceptible to a temperature change, but that one is, because as liquids get warm, they expand in volume. So my liter of solution contains a different number of moles at different temperatures, whereas a kilogram is a kilogram is a kilogram. Knowing that some ionic compounds are not going to be soluble in water gives us the opportunity to make them in a pure way by combining salts together in a way that forces something to precipitate. A precipitate is an insoluble compound that is created during a reaction and it falls to the bottom of the container. We've seen earlier from the solubility rules, all nitrates are soluble. So silver nitrate is guaranteed to be soluble in water, hence the AQ state symbol here for aqueous solution. If I combine it with sodium chloride, now most chlorides are soluble in water, but all sodium salts are soluble in water, so I can guarantee that sodium chloride is soluble in water. I can guarantee that silver nitrate are soluble in water, and when I mix them, they do a reaction. Can you spot what kind of reaction that is? That's a double displacement, where the cations change places with the anions, and I make silver chloride. Now most chlorides are soluble, but silver is an exception. So this is now an insoluble solid, and it floats to the bottom of the container, if you can float to the bottom. And the other thing that I make is sodium nitrate. All sodium salts are soluble, all nitrates are guaranteed to be soluble, so this just floats away. I've just created silver chloride in a pure form. Now there's a little more to this, and we're going to expand this balanced equation into something called a net ionic equation. And in order to do that, I have to go through something called a complete ionic equation, which looks a little bit ugly, but sometimes you have to break eggs to make an omelette, and sometimes you have to cause a mess in order to tidy up. Okay, remember that all sodium salts are soluble, all nitrates are soluble. That makes them strong electrolytes. So what I could do to my balanced equation of silver nitrate plus sodium chloride makes silver chloride plus sodium nitrate is expand that into an ionic equation. So silver nitrate in solution actually contains silver ions, cations, and nitrate anions. Sodium chloride in solution contains sodium cations and chloride anions. Silver chloride is no longer in solution, so this stays as its own little entity. And sodium nitrate splits apart into sodium ions and nitrate ions. Now, the arrow in this equation is the same as an equal sign in a mathematical equation. And in math, if you have numbers on both sides of the equation, they cancel out. So that nitrate and this nitrate, which I had inaccurately written down as chloride just a second ago, they cancel out. I've got nitrate on both sides. This sodium and that sodium ion cancel each other out. These are what we would call spectator ions. They float around in solution, not particularly attached to anything, and they don't participate. And what that reveals to us is the net ionic equation, that all of this that's written on the page comes down to. There are silver ions in solution. They meet chloride ions in solution and make silver chloride. So the net ionic equation is the simplified version of the balanced equation. You have to go through a little bit of expansion and messiness to get there, but this is the simplified version. Two of the very important families of ionic compounds are acids and bases. Now, acids are electrolytes. They split apart in solution and they generate ions, but specifically, we want to see acids generate H+. So acids split to make the H+ ion, which is called hydronium. There are 3 definitions of what an acid is. Arrhenius defined the acid as anything that increases the H+ concentration in solution. That's going to be the simplest one for us to deal with right now. Bronsted and Lowry refined that a little bit to say that an acid is actually donating something. It's donating an H+, and that H+ is actually a proton, because it's just the nucleus of a hydrogen. The electron from the hydrogen is gone, therefore the plus charge. So it's just the nucleus of a hydrogen atom, and that contains only a proton. So the Bronsted definition of an acid is a proton donor. By far the best definition of an acid is the Lewis acid definition, that says acids are electron pair acceptors. This is not going to be immediately obvious to us. This starts to show up when we plan and map out reactions and we follow the flow of electrons, and it proves that all acids behave the same way. For us right now, Arrhenius is the most important definition. Let's look at the names and chemical formula of some acids. Now, fortunately for us, all acids have the word acid in their name, so identifying whether something on paper is an acid or not is easy. Hydrochloric acid is HCl, sulfuric acid is H2SO4, nitric acid is HNO3, phosphoric acid is H3PO4. There is no easy way of determining how many oxygens are supposed to go with how many hydrogens based around this central non-metal. If you look at everything on the board, all non-metals. The acid part of the periodic table comes from the right-hand part of the periodic table, the non-metal part of the periodic table. All of these acids are what we call strong acids. Strong acids dissociate 100% when you put them into solution. Some acids, however, don't do that. These are what we're going to call weak acids. Sulfuric acid, H2SO4, is a strong acid. If we take one of those oxygens away and make H2SO3, the absence of that oxygen deprives the acid of its acidity. And so sulfurous acid is less good at being an acid than sulfuric. And ic and us are 2 old suffixes that don't have numbers associated with them, just degrees, that ic is more than us. So ic acid contains more oxygen than us acid. Nitrous acid is exactly the same thing. That nitric acid was a strong acid at HNO3, nitrous acid is a weak acid at HNO2, carbonic acid is a weak acid. And the one that's different, because hydrochloric acid and hydrobromic acid and hydroiodic acid are all very strong acids, but hydrofluoric acid, because fluorine is top of the group and very small and very electronegative, not a good acid. Doesn't want to let go of the hydrogen. The opposite of an acid is a base. So while acids put H+ into solution, bases are going to take H+ out of solution. And we have 2 very, very strong bases that are also very cheap. So these two dominate the market, and they are sodium hydroxide, NaOH, and potassium hydroxide, KOH. Pay attention to the spelling of potassium. It's something that students spell incorrectly all the time. And then we have one weak base that props up commonly, and it is ammonia. And ammonia has formula of NH3. Don't get confused the difference between ammonia, NH3, and ammonium, which we mentioned in an earlier part of this video, is NH4+. Remember, ium at the end of a word means positive. So, acids put H+ into solution. But just how much H+ do they put into solution? Well, that's something that we can measure on the pH scale. The pH scale technically is this, that pH equals negative log to the base 10 of the H+ concentration. If you see anything in chemistry written in square brackets, good chance is that's a concentration. Well, what's the log? Log's not particularly well understood by the general public. What a log is a mathematical function that turns big intervals between numbers into small intervals in numbers. One of the things that you can do with your calculator is look at what the log of 0 is. Look at what the log of 10 is. Look at what the log of 100 is. Look at the log of 1,000. And you find that the gap between 10 and 1,000 is a big number, but the gap between the logs of those underlying numbers is very, very small. Here's how this relates to what's going on in the outside world right now. Let's say that there was something, some kind of virulent disease that every couple of days doubles its size in magnitude. Before you know it, you've written your graph to be this size, this scale. Well, before you know it, you're off scale on the graph. And the next day, you'll be here. And the day after that, you're going to be all the way up here. If we take the log of the number that's showing big changes between the numbers, the log scale is flattened. That's why we use logs. So pH is the flattened version of the number that is the H+ concentration. And pH exists on a scale between 0 and 14. Down here at 0, things are very, very acidic. In the middle, at 7, they're neutral. They're neither basic nor acidic. And up at 14, they're basic. At 1 or 2 pH, we have things like the contents of your stomach. Stomach acids are at pH 2. Depending on how much phosphoric acid and citric acid is in your carbonated beverage, your soda might have a pH of 3 or 4. The fruit juice that you're drinking might have a pH of 4. Milk has a pH of around 6. Pure water has a pH of 7. Blood has a pH just inside the basic. It's about 7.4. Egg white's about 8. Soap depends on what brand it is, but maybe 9 or 10 is reasonable. And then the household cleaners, bleach is about 12, and drain cleaner can be way, way up there at basic. Okay, we'll do a calculation later. Acids and bases undergo reactions called neutralizations. And it turns out that all acid-base neutralization reactions are fundamentally the same thing. That an acid plus a base makes a salt plus water. Here I have hydrochloric acid and sodium hydroxide combining to make sodium chloride and water. Hydrochloric acid is in solution. It is an aqueous salt. Sodium hydroxide is in solution. It's aqueous. The salt, sodium chloride, is in solution. But water is not part of the solution. Water is a liquid. And so it is its own little covalent molecule. What we need to do now is make a complete ionic equation out of this balanced equation and then define what the net ionic equation looks like. So I've taken my balanced equation and I have expanded it to be a complete ionic equation. But the HCl is a strong electrolyte and has separated into H plus and Cl minus. The sodium hydroxide is a strong electrolyte and has separated into NaOH plus and OH minus. The salt that I have generated is a strong electrolyte and has separated into its component ions, but water is a covalent molecule. And when I look to get rid of the spectator ions, I have a chloride here and a chloride there. They can go. And I have a sodium here and a sodium there. They can go. It turns out that acid puts H plus into solution. There is no H plus in my product because the base has taken the H plus out of solution. All acids are a method of delivering H plus into solution. And it didn't matter, look, the chloride or the nitrate or the sulfate is no longer in my reaction. So it doesn't matter whether I used hydrochloric acid or nitric acid or sulfuric acid, all acids are going to give the same results. And it doesn't matter whether I used sodium hydroxide or potassium hydroxide or magnesium hydroxide, it doesn't matter. The metal ion doesn't make it into the final reckoning of what's going on in this solution. The net ionic shows me the acid puts H plus into solution, the base takes it away. I've generated water. Water is an exceptionally strong, stable molecule. 70% of the planet's surface is covered in water. If you can see a reaction that generates water, that reaction is probably going to happen. Okay, let's look at some calculations based around concentration. The first we're going to start with is, given a mass and a volume, find a concentration in terms of molarity from those. 6.50 grams of sodium sulfate is dissolved up to 125 milliliter solution. What is the molarity? We need to know that moles is mass divided by formula mass, and we need to know that molarity is moles per liter. Now, the way I've got it written out on the board is broken down into those two equations. I'm solving for those two equations separately, but when I'm done, I'm going to go back and we'll do it the dimensional analysis way, in which I solve for the final answer all in one big equation. Okay, so moles is mass divided by formula mass. The mass is in the question. The formula mass of sodium sulfate is something we have to figure out. And we have to figure it out all the way back from the formula, because all it says in the question is sodium sulfate. Here's where you would start. You know that sodium is in group 1. Group 1 metals make a 1 plus ion. Sulfate is in that list of oxoanions that we had no option to do but memorize. And it is SO4 2 minus. That means I need 2 sodiums for every sulfate. The formula for sodium sulfate, therefore, is Na2SO4. Remember, the subscripts only multiply the atom that immediately precedes them. So the number of moles is the mass of sodium sulfate in the question, 6.50 grams, divided by its formula mass. So I look on the periodic table. The atomic mass of sodium is 23, so I'm going to need two 23s, and I'm going to add to it the atomic mass of sulfur, and I'm going to add to it 4 atomic masses of oxygen. Remember, the formula mass is the sum of all of the individual atomic masses in the formula. So the number of moles of sodium sulfate is 6.50 divided by 142 grams per mole. The grams cancel, the per mole travels to the top, 0.045 moles. So I have a mole amount. I can now put my mole amount in my molarity equation. Molarity is moles per litre, specifically litres. My question doesn't have the volume in litres, the question has the volume in millilitres. And I have to do the conversion that there are 1,000 millilitres in a litre. So each of those millilitres is 1,000th of a litre. The molarity is the number of moles divided by litres. And 125 millilitres is 125 divided by 1,000. That gives me an answer of 0.366 moles per litre. We capitalize the M for moles per litre, or molarity. That same equation performed by dimensional analysis looks like this. In dimensional analysis, what we do is we figure what it is that I want at the end. What is my answer? And the answer is moles per litre. So I'm going to set up the numbers in one big equation so that the units in the question lead me to the correct answer. 6.50 grams is given in the question, and I know that 1 mole of sodium sulfate would weigh 142 grams, and setting it up this way makes the grams cancel. But that mole is not going to cancel by anything else that's in the question, and so will carry through. I know that 1 litre is 1,000 millilitres, so my litres are here in my numerator, and my question gave me 125 millilitres as a volume. So now those millilitres have cancelled, and my answer is in moles per litre. So when I take 6.5, divide it by 142, and then multiply it by 1,000, and then divide it by 125, I get the same answer, 0.366 moles per litre. Okay, here's a second calculation that asks the question backwards. This one actually is more realistic in the kind of thing that we do more day to day. You're required to make a 250 milliliter solution of 0.200 molar sodium hydroxide solution. What mass of sodium hydroxide should you dissolve? So we know 2 equations. They are molarity equals moles per litre, and we know that moles equals mass divided by formula mass. This question is asking us to get to that, the mass. In order to get there, I need moles. In order to get to moles, I need to convert the molarity that's in the question and the number of litres that's in the question, currently as millilitres, into moles. So I'm going to rewrite molarity equals moles per litre as moles equals molarity times litre. If I move the litres across the equal sign, it goes from being a denominator to being a numerator. Moles is molarity times liters. And remember, there's 1,000 milliliters in a liter. And I only have 250 milliliters of solution to be made. 250 milliliters is quarter of a liter, 0.250 liters. So the moles of sodium hydroxide required to make that solution are equal to its molarity, 0.2 moles per liter, times its volume in liters, 0.25 liters. That is 0.05 moles. Now moles equals mass divided by formula mass. I'm going to rearrange that in a way that isolates and gives me mass. Mass equals moles times formula mass. So the mass of sodium hydroxide required in this reaction is the moles of sodium hydroxide, which I just found, times the formula mass of sodium hydroxide. Well, sodium hydroxide is NaOH. That's a 23 from the periodic table for the atomic mass of sodium, a 16 for the atomic mass of oxygen, and a 1 for the atomic mass of hydrogen. That's 40.0 something. So 0.05 times 40.0 something gives me 2 grams. I need to dissolve 2 grams of sodium hydroxide into a flask and top it up to 250 milliliters in order to make the required solution at 0.2 moles per liter. Here's another common calculation. We're going to do a dilution. If you have a stock solution, 250 milliliters of 0.200 molar solution of sodium hydroxide, and you pipette out 10 milliliters of that stock solution into an empty flask, and then you top that flask up to 250 milliliters, what is the new molarity? So schematically, I've got on the board what we're looking at. I have my stock solution here. There are 250 milliliters of a solution that is 0.2 moles per liter. I'm going to pipette out 10 milliliters of that into a new flask, and then I'm going to dilute that up to 250 milliliters. And I want to know what the concentration inside this flask is. Well, it turns out that we saw in a previous example that molarity times liters is moles. And because that's going to be the same on both sides, it turns out that the molarity times volume that we start with is equal to the molarity times the volume that we finish with, so that M1V1 equals M2V2. So the numbers are all in the question. All I have to do is rearrange this so that it gives me the number that I'm looking for. But what I'm looking for is the molarity at the end. We'll call that one M2. If M1V1 equals M2V2, then M2 is M1 times V1 divided by V2. I take that V2 and move it across the equal sign, it becomes a denominator. It moves from being on the top to being on the bottom. Okay, then all I have to do is put the numbers in. These questions usually come with a little bit of a trick. And the trick was, we told you at the beginning that there were 250 milliliters of the stock solution. That doesn't matter. That doesn't matter. Because I didn't use that 250 milliliters. What I used was the 10 milliliters. So I took 10 milliliters of 0.2 molar solution and diluted that 10 milliliters up to 250. So there's my molarity that I started with of the stock solution. That's my 10, the volume that I started with. There's my 250, the volume that I finished with. Now, in some calculations, it's important to turn milliliters into liters. In this case, because we're dividing two volumes, those milliliters cancel each other out. So if I turned them both into liters or left them both as milliliters, it makes no difference. M2 equals M1V1 over V2 gives me an answer for M2, my new molarity of 0.008 moles per liter. Here's a final calculation. Let's find the pH. What is the pH of 0.150 molar nitric acid? No volume in the question. Don't need it, because the pH of a liter of that acid would be the same as 10 milliliters of that acid. The pH is going to be independent of amount. So here's nitric acid, and it's a strong electrolyte. When you put it into solution, it separates, dissociates, and ionizes 100%. So if I started out with 0.15 mole per liter of nitric acid, what that really means is in solution, there's no nitric acid at all, but I have 0.15 molar H+. I also have 0.15 molar nitrate, but I don't care about that. That H+ goes directly in this box because pH is the negative log to the base 10 of the hydronium ion concentration. So pH equals negative log to the base 10 of 0.15. The pH of this acid, a strong acid, comes out between 0 and 1, where we would expect strong acids to have their pH.